Okay. Taylor, can you hear us out there?
Yes.
Let's see. We are in chapter 7 still, right? I keep thinking we're going to get through it more, but we're not really getting there. Hopefully today we'll finish up chapter 7, even though it seems like we've just barely started it. But as I said before, we're done with most of it. We're done with section 1 is the part that has most of the math in it. So in section 1 of chapter 7, we have learned about work and the mathematical calculation of work, because work depends on the path that you take. Work is the amount of energy that a force imparts to an object to make an object move. So in other words, it's the amount of energy required to make something move. And that energy is always given to the object by another object applying a force to it and doing that work on it, causing it to move. But how much energy is imparted does depend on the path that it takes. In other words, the distance that that force is being applied over the course of that movement. So that's why the calculus was needed, because the path that you follow when you're pushing something is not necessarily a straight path or a constant path. The force is not constant. The path is not constant. The direction is not constant. All these different things are not constant. So you have to do an integral. You actually have to do a dot product as well to make sure that the force and the displacement vectors are in the same direction. So there's a lot of math involved, and that's what that was all about as we did all that calculation and stuff. In the end, there are millions of different ways to work this out, lots of different situations that you can apply this. There's another example of this towards the end of the first section is with a spring. If you're doing work with a spring, the force changes depending on how much you stretch the spring. The more you stretch the spring, the more force is needed to stretch the spring. And so you have to put in the force function for a spring, which is the spring constant times x, and there's a negative sign on there, which is why I get the negative kx here for that force. The k comes out because it's a constant, and negative comes out because it's constant, but you still get an x inside here. And then you get x dx and you integrate and so on. So it's different for every situation. You just have to be aware of that. As always, if we're thinking about integrating is taking if you're looking at it graphically, and your function is on the y axis and the function is plotted on the y axis, your independent variable is plotted on the x axis, then the integral gives you the area under the curve. And so in some situations, you can actually estimate the work done by estimating the area under the curve. And if the area that you're measuring, or the curve that is the function, is above the x-axis, then you're going to have a positive area or a positive work being done. But if the work is below the x-axis, that will be a negative area, which is a negative amount of work being done. And that can happen. This is actually what the spring force function looks like. It's a line where the slope of the line is actually equal to the spring constant. And it does have a positive and a negative situation to it, depending on what you're looking at. You can either do work on the spring, or the spring can do work on you, and you can push it and pull it. So there are different things that can happen with springs, and that all plays into the math. different ways. So here they do an example of that, and they're stretching it from its equilibrium position. They want to actually know what the spring constant is. So they're telling you everything that you need to know, how much work is being done, how much it's stretched, and then they want you to calculate the spring constant required to do that. And you're just using all these equations and solving for K instead of solving for work. This is the one where they do that right here, equation 7.5. So, and we could go on and on and on. There's so many different ways that you can apply this, but we need to get on with life. So we're going to move on to section 2 and learn about kinetic energy. Well, if work is this energy that you give to something by applying a force to it, making it move, the energy of movement itself is the energy is where that energy goes. When you do work on an object to make it move, that work energy becomes movement energy, which we call kinetic energy. And so so we actually know that kinetic energy is equal to 1/2 mv squared, but we can actually show it as well. We can show that that is the case. And we show that that is the case somewhere here. I think they do it after they do their first examples, and I'm trying to remember where exactly they do it. I would prefer to do it before, so I'm going to do it before. So here we have our work, the mathematics of work, where if we take the derivative of the work, it's equal to mass times, let's see here, is that what we want to do? Here we go. Newton's second, we start with Newton's second law, and that's the net force equals mass times acceleration, which is dv dt, right? That's your acceleration. And then if we take the derivative of the work, the derivative of the work is equal to the force times the force with the dot product with the displacement. So this is the force is mass dv dt, and the dot product with the displacement vector right there. So this dot product here defines what each little piece of the work is. Then we can go from here, we can actually redistribute things a little bit. And this kind of makes mathematicians angry because they think you shouldn't be able to do this. But the fact of the matter is that in reality, in the real universe that we live in, you can do this. So we just do it in physics. Since we invented calculus, we can do whatever we want with it, despite what mathematicians think we can and can't do with it. So what we do is we take this time derivative that's with the velocity to make this acceleration, and we just put the time derivative with the displacement. So this displacement becomes a v. This dr dt is now the derivative of the displacement with time, which is velocity. So we have the mass times the derivative of velocity times the velocity again, right? So it's mv dv. Well, this is the derivative of work, and so if we take the integral of both sides, we actually get rid of both of those complete derivatives, and we end up with the equation 1/2 mv squared right here when we do the derivative. And it's the 1/2, and when you do work on an object, it's not, the work is not equal to the kinetic energy, it's equal to the change in kinetic energy, because when you do the integral, you're actually taking 1/2 mv squared at point B minus 1/2 mv squared at point A. So it's your ending point minus your beginning point. So it's the difference in the kinetic energy. And this actually gives rise to a theorem that we call the work energy theorem, but it also gives rise to the idea that work energy becomes this new kind of energy that's related to the speed of the object, or the v squared in that. And it's also related to the mass, but it's really related to the speed because it's got v squared in the equations. And that's where this 1/2 mv squared comes from. It's from that derivation. So I wanted you to know that we're not just pulling this out of thin air. So kinetic energy is movement energy. It is actually energy that is manifested in the movement of mass. If something is not moving, it has no kinetic energy. If something is moving, it has kinetic energy. We need to remember that kinetic energy is like work energy. It's not a vector. It has no direction. And kinetic energy is even different from work because work could be positive or negative. If you're doing work on something and you're speeding it up, then that work is positive because you're adding energy to that system. But if you're doing work on something and you're slowing it down, you're actually doing negative work on that system because you're taking energy away from the system. So work has positive and negatives, but kinetic energy does not. Kinetic energy is only positive. It's 1/2 times mass. 1/2 is always positive. Mass is always positive. And it's the velocity squared, or the magnitude of the velocity squared. So it's the speed squared, which is always positive. So kinetic energy is always positive. Now, a difference in kinetic energy can be negative, but each individual kinetic energy of a system at any point in time is always going to be a positive number. Earlier we learned about momentum being related to Newton's second law. And it's also true here. Momentum is equal to the mass times the velocity vector. And it turns out that if you take 1/2 times mass times the momentum squared over mass, you get momentum squared over 2m. And that actually is the same as 1/2 mv squared. And that's totally fine. But that's taking into account that momentum is a vector. And in this equation, we're using the momentum as a scalar. So in other words, we're looking at the magnitude of the momentum. So momentum is only related to this stuff in its magnitude, which only takes into account part of what momentum actually is, just to see that relationship. Okay, now setting all that deep math stuff aside, let's actually use this idea of kinetic energy to learn some things. So we're going to calculate some kinetic energies of different things. An 80-kilogram athlete running at 10 meters per second, right? So if you're 80 kilograms and you're running at 10 meters per second, your mass is your 80 and your V is 10, of course. We plug those in and we get 4 kilojoules or 4,000 joules of energy. Well, 4,000 joules is about 1 food calorie. Okay, so that's how much energy your movement holds as an 80-kilogram person. Okay, that's an 80 kilograms is pretty average, I would say, for a human. And 10 meters per second, that's running pretty fast. That's like a full-out sprint for a good athlete. 10 meters per second. And most people cannot run that fast for very long. In fact, I would say most people can't run that fast at all. Yeah, I mean, it's really fast. It is smoking. Very few people can do that. People that can do that are usually people that have good athletic abilities, at least good and probably, if not excellent, athletic abilities. But that's not very much energy. That's 1 food calorie of energy that is bound up in that movement, right? So it's really just not that much energy. Let's take a look at the crater in the Yucatan, which is one of the largest impact craters on Earth. It's thought to have been created by an asteroid traveling at 22 kilometers per second, so 22,000 meters per second, and it released 4.2 times 10 to the 23rd joules of kinetic energy. Well, that's a lot of food calories, right? Well, let's see, what was its mass, right? It's in this thing we've got mass is part of the equation, so we can solve it for that, and it's mass equals 2 times the kinetic energy over the velocity squared. Plug in all those numbers that we know, and we get 1.7 times 10 to the 15 kilograms, which is a large amount of mass. It's a very large amount of mass. Okay, but notice 1.7 times 10 to the 15 is not even 1% of the kinetic energy. In other words, a very tiny amount of the kinetic energy came from the mass. That's 1/1,000,000% or less. It's like 1/1000,000,000 of a percent of the mass of the kinetic energy, 10 to the 15. So only 1/1000,000,000 of the kinetic energy was because of the mass. The velocity was 22,000 meters per second. But when you square that, that becomes huge. 400 million essentially is what it becomes, right? So it becomes a much bigger deal there. The velocity, in other words, plays a much bigger role than the mass in these things. And then you have the kinetic energy of the last one, which is nuclear reactors, thermal neutrons traveling at 2.2 kilometers per second play an important role. What's the kinetic energy of such a particle? So a neutron has a mass of 10 to the minus 27 kilograms. So a tiny, tiny thing. And here we have 1 half times the mass, 1.68 times 10 to the minus 27 kilograms, times 2.2 kilometers per second squared. These ones have an energy of 4.1 times 10 to the minus 21 joules. Now that's way smaller than either of the two previous energies, right? But that neutron actually has enough energy to dismantle DNA. It actually has enough energy to take apart DNA molecules, which is why it's dangerous to the human body. Because if you start taking apart your DNA, your body has to go back in and fix the DNA. And if you take apart enough DNA and your body has to fix a lot of DNA all at once, it has a higher chance of making mistakes, and those mistakes can become cancerous. Those mistakes can become mistakes that your body replicates, in other words. And that's what cancer is. So that's why you don't want to be out in the sun and get sunburns. Sunburns are essentially just damaged molecules in your body. You know, or you could think about it as damaged cells, but each one of those cells is made up of many molecules. And some of those molecules are DNA molecules. And if you damage enough DNA molecules in the sun, which the sun does, you know, the ultraviolet light from the sun has enough energy to do that, then your body will make mistakes in repairing them more often, and you have a higher chance of having a mistake that propagates through your body as cancerous cells. Cancer really is a very simple energy issue at its most fundamental point, where it starts. As it progresses, it becomes more and more complex because it becomes more biological.
What about in certain scenarios like I think it was the second Vietnam War accident, where it's so much radiation that instead of messing with your DNA and causing cancerous growths within like a certain amount of time, that literally you just like start melting. Right?
Well, yeah. So if you have enough high energy particles and enough high energy radiation, like gamma rays are not particles per se. It can be considered particles, I suppose, but gamma rays are more like high energy light waves that have the same amount of energy or more energy than even like the neutrons. Those particles aren't just taking apart the DNA. The DNA is one of the most fragile molecules in your body. It's much easier to take apart. It's bigger molecules tend to be less stable. It's the biggest molecule that we know of, in fact. But if you get enough energy, it's literally is taking apart all of the molecules in your cells, which is what sunburn is. The sunburn it's taking apart the molecules in your cells, and your cells literally fall apart. That's why you have skin falling off. That's why your skin is red, because you've burst a lot of different things in your skin, and it's irritating, and there's all kinds of problems going on there. Your body reacts to that. That's why there's pain in your skin. All these things have broken, and it's causing the pain receptors to fire, because that's dangerous to the body. So pain receptors fire as a warning. So all these things happen in sunburns, but if you have enough of this stuff, enough energetic stuff hitting your skin, it literally just takes apart everything. And it takes apart the most fragile things first. And one of the most fragile things in your body, well, some of the most fragile things in your body are your internal organs, particularly the heart, the organs that are not muscle organs. So the liver, the spleen, the kidneys, all of those things, they come apart very easily. Your intestine, the intestinal lining, lots of things are very soft tissues. They're very delicate, and any amount of energy will literally just take them apart, and then you're just liquefied. Essentially, it's just liquid stuff in your body. And it sounds disgusting, and it is disgusting. And it's a terrible way to die. Because if you get that much, if you get radiation to that extent and it just dissolves your liver, for example, you're dead. You're a walking dead person. And it will take you a few hours to actually die. But literally, you've been melted on the inside. And it does damage to other things in your body, but it goes through your body and damages the weakest things first. So yeah, it's not good. And it not only does it like do damage to the liver, this high radiation stuff, but it does damage to smaller things in your body that cause your body to essentially, well, it's a terrible thing. I probably shouldn't go into great detail. And it's not very likely that it could happen to a human being. You have to literally be like, you would have to like open up a nuclear bomb and actually like grab onto the thing that makes it all nuclear, the plutonium inside, and like hug it and sleep with it overnight or something like that. It would take that amount of radiation to cause this kind of damage. There are only a few instances of this ever happening. Actually, there's rumors that it happened in the Manhattan Project in New Mexico when they were trying to build the nuclear bomb, the first nuclear bombs. If this kind of thing is interesting to you, I recommend there's a movie made about it quite a few years back called Fat Man, Little Boy. Actually, there's a copy of it in the library, DVD if you're interested. You can also watch it online several places. It's a well done movie that kind of catalogs a lot of the politics and science behind the Manhattan Project. And there have been other incidents where it's happened, mostly in military situations, where people were doing testing and things at close proximity to this stuff.
Have you ever heard of the Demon Core?
Yeah, that's another one. I'm not actually familiar with it by that name. What is this?
It's like I think it was partly a part of the Manhattan Project, where it was one unused uranium, might have been uranium or plutonium core.
Yeah,
They
that's the
decided
one.
to-
That's the one that happened at New Mexico. I've never heard of it called Demon
after.
Core.
I think the Demon Core's, or there were two different incidents. I think one was like maybe the Manhattan Project specifically, but there was a second one because it was the same like big chunk of plutonium that did it. The second one was really fun because they accidentally the amount of plutonium they had was separated by a screwdriver, and they accidentally either slipped out of someone, took it out, and they shouldn't have, and then it became super critical. Just blasted like 4 people in the room with
Yeah,
a
that's
massive amount of radiation.
Yeah, that's the Demon Core one. Yeah.
Yeah.
There was another one. I think someone accidentally.
that one is actually portrayed in the movie Fat Man, Little Boy. And so that's the one that I was talking about. I'm not aware of any other one that happened, and that did happen during the Manhattan Project during World War II, I believe.
I thought it happened after, like a little bit after.
I don't think so. It's possible, but I'm not sure. I'm not sure about the history behind it.
I know there was another incident with the same core where someone accidentally dropped a brick on it.
Yeah, that's possible.
Just a whole brick. I think it was some sort of like reflective material, but still.
So yeah, and it's interesting because you don't even have to have a critical mass of plutonium to do this. If you like, machining plutonium is very difficult. It's a very hard metal, and it has to be machined in a neutral gas, because if you get small pieces, dust particles and ribbons of plutonium, it actually flash combusts with air, with oxygen. And when it combusts, it releases all kinds of poisonous radioactive gases into the air, and breathing just a little bit of that goes directly into your bloodstream and causes all kinds of problems. These kinds of things have happened, but they're so rare and so unlikely, because you really have to be in a position where you're handling this stuff with your hands, and nobody does that anymore. They don't do anything like this anymore. Nobody comes close to this stuff anymore. And they've also created an alloy of plutonium with, I think, polonium or something like this. They've created an alloy that is much more stable, that is used in the bombs now rather than just pure plutonium. So, and that's a good thing, because the bombs made with pure plutonium actually had a very short shelf life. They were like bananas. They would go bad after a very short amount of time. They wouldn't be useful as weapons anymore, which maybe it wouldn't be a bad thing. I prefer the weapons didn't exist at all, but the world we live in unfortunately requires that we have these weapons. And anyway, the point is that that this energy does come down to, you can think of it in terms of kinetic energy. Literally, that's what we're talking about here. It's the movement of particles has a lot to do with the amount of damage it can do, or things that it can do, and that's carried in the movement of these particles in many cases. So anyway, here we're gonna calculate a person's kinetic energy. Well, get something in my mouth. In this case, we have a person walking in a subway car, and they're walking at a speed of 1.5 meters per second relative to the subway car. The subway car is moving at 15 meters per second relative to the tracks. We want to know what the person's kinetic energy is relative to the car. Well, can kinetic energy be relative? Well, yeah, it can be. Your relative kinetic energy will tell you the amount of energy that you have available to do things relative to that thing that you're measuring it to. So the person walking inside of the car, their kinetic energy is a certain amount of energy that they can use to do things in that car. For example, if they wanted to squish a pillow at the end of the car, there's a big pillow at the one end of the car, and they walk toward it 1.5 meters per second, their kinetic energy can be turned into deformation energy to deform that pillow or to squish that pillow, right? It's essentially work being done on the pillow to change its shape and size or whatever else. But the person's kinetic energy relative to the ground is going to be much different, because the car is moving. So if the person jumps out of the car and jumps into a pillow at the station, they'll be able to do a lot more deformation of the pillow, because they'll not only have their kinetic energy, but they'll have the train's kinetic energy as well. And that could result in more kinetic energy than the train had if the person's walking in the same direction the train's moving, because then their velocities add together to be a bigger total velocity. Or if the person is walking in the opposite direction that the train is moving, that results in less kinetic energy than the train had, than they would have had with the train's velocity. Now, of course, the train has much more kinetic energy because its mass is much bigger. But you kind of get the idea that kinetic energy can be relative. And so they go ahead and calculate these, and it's not very difficult. It's 1/2 mv squared. If you want to get the total kinetic energy, you have to add the kinetic energy of the car, and then you have to add that to the kinetic energy of the person relative to the car, right? So that's what they are using these subscripts for again. Let's see. So the velocity of the person total is equal to the velocity of the person relative to the car, plus the velocity of the car relative to the tracks. I'm assuming that's what that means. And that can be positive and negative because it's vectors, right? So you choose a direction for positive, and then your velocities are positive and negative, depending on which direction they're going. And here they calculate the two different kinetic energies depending on which way the person is walking relative to the train moving, and using those two relative velocities and so on and so forth. Of course, if the person is not moving at all relative to the train, their kinetic energy relative to the train is 0, right? So kinetic energy. Here we're doing some kinetic energy of a baseball, I guess. 1/2 mv squared once again. So this is the horizontal speed. So here they're actually talking about the horizontal kinetic energy of the base, or the basketball rather, not a baseball. So they're only looking at the horizontal speed or the horizontal component of the speed, which is fine. I don't know that anybody does that really. The translational kinetic energy of a molecule. So a molecule moves very, very quickly and has very, very small mass. It's quite a small amount of energy for the kinetic energy of the molecules. If you add all the kinetic energy of the molecules moving at that speed, it becomes a lot of energy. But that doesn't necessarily tell you the whole picture, because molecules are always trading kinetic energy with each other as they run into each other, as they transfer it all around. So the kinetic energy doesn't all exert itself in one direction to do any work, usually like in a basketball. So that's kind of goofy, but that's all right. Here in the last part of this one, they're calculating how fast would a basketball have to travel to have a kinetic energy equal to all the kinetic energy of its molecules. 76 meters per second. So we have to move at 100 miles an hour, 150 miles an hour. It's kind of ridiculous, but whatever.
In relation to the earlier thing we're talking about with the first doing at 10 meters per second.
Yep.
We're talking about that. I looked at Usain's Bolt record, and his was 10.44.
Yep.
So basically the Olympic cube.
Yep. Well, there's a big difference between 10 and 10.4, actually. That's the difference between a 10-second 100 and a 9 point whatever he had, second 100. A lot of people can run a 10-second 100. The number of people that can run 10-second 100 meters is uncountable. There's hundreds of thousands of people on earth that can do that. The people that can get it into 9 point something, that's a lot different. And it's like 3, 4, or 5 body lengths or something like this. It's a lot of difference. And he's probably 10.4 is
6 point something feet tall, like 6, 7, I think.
Yeah.
Big.
Yeah, and 10.4 meters per second is pretty close to 25 miles an hour, pretty close to that, somewhere in there, which is about the fastest speed that a human has ever run. So yeah, it's kind of interesting. All right. Okay, let's get on with it. Here they do this derivation that we looked at earlier, and that's great. This derivation leads to this equation right here, which is the net work done between 2 points is equal to the difference in the kinetic energy at those 2 points. Right? And so, and that is completely separate from the calculus in the middle. All the calculus is done in the middle, assuming that the masses are constant, but assuming that the velocities are going to be integrated essentially. And this is that they're changing, in other words. So so this is pretty general as long as the mass of your system isn't changing. I actually think it's even true if the mass does change in certain circumstances. But anyway, we're going to take it as this, but this equation results in this very simple theorem that has no calculus involved. It's just the network is equal to the difference in the kinetic energies. The kinetic energy at point B minus the kinetic energy at point A tells you the network done between those 2 points. You can still use this equation with calculus if you want to calculate the work using calculus. But if you already know the beginning and ending kinetic energies, you don't have to use any calculus. So it's a really nice theorem, really nice equation. And what it tells us practically is that work creates a change in kinetic energy. When you apply a force on an object and move that object from point A to point B, or that object moves from point A to point B while you're applying a force to it, then you will get a change in kinetic energy. It changes the kinetic energy somehow, which means really that it's going to change its speed somehow, right? So that's a great theorem. Very simple, very straightforward, very easy to calculate. Let's see, what are they doing here? In this next section, I actually would prefer to do an example really quick that doesn't involve what they're doing there. So yeah, let's do this one right here. Here we have a bullet that's being stopped by a block of wood. So you're shooting this bullet. They tell you the mass, they tell you the velocity, and they're telling you that it can penetrate 8 1-inch pine boards, which are thick each with a thickness of 0.75 inches before it stops. So what have they told us? They've told us mass, velocity, and the distance that the force is applied for stopping it, right? The stopping distance. Well, according to Newton, according to the work energy theorem, the net work has to equal the change in kinetic energy. The change in kinetic energy is the final kinetic energy, which is going to be 0 in this case because it's coming to a stop. And then you subtract off the initial kinetic energy, final minus initial, and that would be 1/2 m times the velocity of the bullet when it was fired, right? And that has to equal the net work. So that's what this equation means. The net work is going to equal the force, the average force to stop the bullet times the distance it takes to stop it. And they told us the distance. So this equation is the thing we need to solve for the force, because we know what the stopping distance was, and we know what the initial kinetic energy is. Now there's a negative sign in there because the force stopping the bullet is in the opposite direction of the direction it's moving, or the distance that it moves. And so remember when we had the cosine of the angle thing going on in there, the cosine of 180 degrees is -1. So that's why the negative comes in there from that dot product of the work. But anyway, we solve it for the average force and we get the kinetic energy over the stopping distance, 1/2 mv squared over the distance. All of the numbers we've been given, we can just throw them in here, a few little simple conversions, and we end up with 960 newtons of force, right? We could have, it's easy to use kinematics to solve this equation, but this is actually quicker, I think. This is a much quicker way to do it. And it turns out that when you're using energy to solve kinematic equations, it's often much quicker. This is a one-dimensional situation, but energy has no dimension to it, right? Energy is completely scalar. So in a one-dimensional situation, you're using 1, maybe 2 equations in kinematics, but you're only using 1 equation and no directions really, except for the dot product and the work. It's a really simple thing. If we go to 2 dimensions and you're in kinematics, you're obviously going to be using at least 2 equations, but sometimes even more. And it all of a sudden becomes more complicated because you end up with trigonometry and all kinds of stuff involved. So using energy to solve problems is often much easier than using kinematics. Now let's backtrack a little bit and go back to this section where we talk about moving in. In this section, we're going to talk about the work energy theorem in the y direction as we move up and down in a gravitational field. Well, when we move up and down in a gravitational field, let's see here. Let me look at something real quick. When we're moving things up and down in a gravitational field, we are moving against a force that is already there. And assuming that we're not going to accelerate things up and down in that field, we're just going to move them without accelerating them. That means that the force that we have to apply has to equal the gravitational force. And let's draw a picture of this really quick. Let's say that we have a box that we're going to lift. Here's our box. And we draw our free body diagram. The weight of the box pulls it downward towards the earth. And we're going to apply a force that is equal and opposite to that upwards so that we can move the box upward. Now we're not accelerating the box upward, we're just moving it. So we only need these 2 forces to be equal. If we wanted to accelerate the box upward, then the upward force would have to be greater than the weight. But these are just going to cancel out, and they're going to total, we're going to have a grand total of 0 net force, no acceleration, but we can still have an upward velocity, right? it honestly doesn't really matter if we accelerate it as long as we start from, as long as we bring it to a stop eventually, and then the average velocity will still be constant, or the average force will still be zero, in other words. But we're going to assume it this way for now, just for the sake of being consistent, I suppose. When we do this against gravity in the gravitational directions, then we have to make this equation that is the sum of the forces equals 0, right? And we have our weight, which is down, and our force, which is up. That equals 0. That means our force upward is equal to our weight downward, which means our force is equal to m times g, right? We have g being introduced into our force equation because of Newton's second law here. And when we were dealing with kinematics, the kinematic equations, we actually just replaced acceleration with g. This is the last kinematic equation in there, and we replace the acceleration with g here. But this is actually equivalent to the what were we just talking about? The work energy equation, right? Here's the v squareds that are in the work energy equation. The 1/2 is here too. If we divide everything by 2, we get rid of this 2, and we get a 1/2 here, and we get a 1/2 here. So the 1/2s are in there. Those are the 1/2 v squared, 1/2 v squared. If we multiply everything by the mass of our object, we get 1/2 mv squared, and we get m times g over here. There's that mg, the force is mg, so this becomes force. And this right here is the distance times the sine of theta. So this part right here becomes the work. That's the work. And this over here becomes, these over here become the kinetic energies. And if we solve this equation for the work, what we get is the net work. Solve everything for the last thing on this equation. This is the net work over here. And we get kinetic energy final minus kinetic energy initial,
So
which is the work energy thing.
Sorry, just make sure I'm hearing right. You can interchange the velocity final, velocity initial, kinetic energy squared final, kinetic energy initial final squared.
No, we're not exchanging it, we're just creating it. Let me do it again really quick. This is actually a kinematic equation. This is the last kinematic equation. Final velocity squared equals initial velocity squared plus 2 times the acceleration times the change in distance. Now, in this case, we're looking at the change in distance in the y direction. So that's why we have the sine of theta on there. That gives us the change in direction in the y direction, right? And this is our change in direction. This would normally be r, but we're calling it s for some reason, I don't know why. But this is 2 times a times delta x, essentially, or delta y. So this is a kinematic equation, right? However, if we multiply everything in here times m, times the mass of the object that's changing the velocity, 2m, do we get mg in here, right? And then we divide everything by 2. It puts a 1/2 here and a 1/2 here and a 1/2 here. This 2 by 2 becomes just 1. And what we're left with right here is m times g times distance times change in r or change in s or whatever you want to call it, times sine theta. Well, this right here is equal to the work, because work is equal to force, which in this case is m times g, dot product with delta r. And the dot product gives us the force times delta r, which in this case is delta s, which is s final minus s initial, times the angle between them, sine of the angle between them, sine theta, which is exactly what that is. So this thing right here is the work now, because we've divided by 2 and we've multiplied by mass. And these over here are 1/2 mv squared and 1/2 mv squared, initial and final. So these two things are actually, if we subtract 1/2 mv initial squared from both sides and put it on this side, we get the change in kinetic energy equals the work. which is the work energy theorem, right? So all we're doing there is we're showing that we're showing another way that the kinetic energy, that the kinematic equations are true. They're true through the work energy theorem. And we're also showing that the work energy theorem is true by connecting it to the kinematic equations. This is something that scientists always try to do when they find something new, when they discover something new, they try to tie it in using mathematics to something else that they've discovered. So they discovered kinematics separately from discovering the work energy theorem, but they tied them together using simple algebra. And that actually shows the continuity between the two theories, because we've used mathematics to develop these theories. They better agree if you try to connect them mathematically. If they don't agree when you try to connect them mathematically, one or both of the theories is wrong. If you believe that mathematics has something to do with nature, if you believe nature, follows mathematical constructs, which we do believe that. So anyway, this is great because now we can know for ourselves that this idea of energy seems to be holding up to our other theories about nature, the things that we've observed in nature. This is unfortunately something that is not well known to people. Most people think that science is just people observing the universe around them and coming up with these ideas of how it works. But it's not just that. I mean, that's part of it, but it's a very small part of it. The ideas must be tenable. You must be able to connect them to other ideas, and all these ideas should support each other. And when they don't, that reveals a gap in our understanding. And there are many such gaps, but we're trying to close those gaps. That's what science is about, closing those gaps, making sure that these things all fit together. So anyway, so here's an example of this that involves lifting things up in gravity, because what this actually tells us is that there's another thing that this equation tells us that we just came up with. On the work side, we had mg times a change in height, essentially, times delta y. That's actually a new kind of energy, because that has nothing to do with movement. It has to do with a different height. So when you move something from a lower height to a bigger height, you actually give it some energy when it's in a gravitational field. And we call this kind of energy, we call it potential energy, gravitational potential energy, because it has the potential to fall back down to the lower height. So in this case, we have this loop-to-loop track, and we're going to lift a ball up to this height at point 1, which is the height is going to be height y1, whatever that is, 10 meters, 5 meters, whatever it is. And then we're going to release that ball, and we're going to assume that there's no friction, there's nothing that's going to remove energy from the system, and we're going to calculate its speed at the end of the track, at the other end here. I think that's what they're going to do. I don't know what they're going to do actually. What do they want us to do here? How high measured from the boss? Oh, they want to know how high it has to be placed up here in order for it to go all the way around the loop. That's what they want to know. Okay. So what they're going to do is they're going to set up the left side of the equation with m times g times the height. That's going to be the potential energy they're going to give it by putting it up at a certain height to start with. And then they're going to say that has to equal 1/2 mv squared here in the loop. It has to be going a certain speed to get through the loop. Well, how do you know it has to be going a certain speed to go through the loop? Well, we do know that in order to stay on the edge of a circle, you have to have a certain amount of speed, right? We know that from the centripetal force. The centripetal force is related to the tangential speed. So this v squared right here has to give us an acceleration that's going to be v squared over r. So we're going to solve this equation, acceleration equals v squared over r, and we're going to solve that for v essentially to get a speed that we need there. When we do that, we're essentially solving this equation here. And this is actually from the free body diagram. You have a normal force from the track, and then you have m times g from the car. And those two things have to add together to be zero in order for it to stay on that loop. So they put all that stuff in together here, and then they're going to solve it for the normal force, which is the force that it's actually going to be pushing with, I guess. The normal, so this ends up being your sum of forces, which is your centripetal force plus the weight, or minus the weight in the case because it's that direction. And then this is all the stuff from the other equation, from the work equation. All that has to be greater than zero, because at zero it stays on the track, but anything greater than that, it falls off the track essentially. And then they solve for that, and this is what they get, that that the height has to be 5 times the radius divided by 2, 5 times the radius of the loop divided by 2, which is just slightly, which means it has to be just slightly higher than twice, or 2.5 times, literally, not just slightly higher, but 2.5 times the height of the loop in order for it to get to the loop, right? Here it doesn't show it nearly that high, but it needs to be quite a bit higher to get through there. All right, so that takes us to the end of that section and introduces you to a new kind of energy, potential energy. The kind of energy that you get when you go higher up in a gravitational field, and you can actually fall down and turn that potential energy into kinetic energy as you fall down from a high height to a lower height. And that is that for today. So we will see you later.
Can you change the homework to Wednesday?
Yeah, we will change it because we'll finish up Wednesday. Yep.
Can I ask a question?
Sure
I
thing.
did send a message about the homework for problem 1. I'm still not quite understanding, because I'm understanding now that like the last 2 answers, like the work done by friction and the net force, are going to be like, I understand what those are going to be. So net force is going to be 0, and the workforce done by friction, the work done by friction is going to be just the negative of the workforce. But I'm still not. I just still can't find the work done by force thing, because
Chapter 7 homework we're looking at.
yep.
Okay, hold on just a second. Let me open it up. Yeah, so in this picture, this is what we're looking at here. You have a sled. We'll just represent it like a box, right? And we have this surface that we're dragging it across.
Yep.
And it has the forces involved, or the pulling force.
Yep.
And then the friction force this way, right? Friction is equal to mu K normal times the normal force. You have the weight of the box and the normal force have to be equal and opposite to each other, right?
Which would be about
M times G.
470.4.
So your normal force is M times G. That means your friction force is mu times M times G, right? And we also know that friction force is negative because we're going to choose this way to be positive.
It's working against the box.
Well, that's not why we choose it to be negative. We chose this way to be positive and this way to be negative, and that's the way it is. The distance now the displacement of the box is positive in this case. So this will be your delta R or your delta X or whatever you want to call it. And it is also, it's definitely positive. And the dot product between these two is going to result in a negative work, right? Because work is equal to, it's equal to the force vector dot product with the delta X vector, because this is only one dimensional.
Mm-hmm.
And since the dot product results in the magnitude of the force times the magnitude of the delta X. So those are just positive, times the sine of the angle between them. Oh, sorry, the cosine of the angle between them. I always get it mixed up. It's actually cosine, right?
I was gonna say I get it mixed up a lot too.
times the cosine of the angle between them, the angle is 180 degrees between them because this one's pointing right and this one's pointing left, right? So that's why you get the negative work, right? Negative F times delta X. So that's where the negative comes from in that case. Now your force in this case is your friction, so it's negative the friction, so it's negative mu K times the normal force, which is equal to M times G. And in this case, G is just going to be 9.8, not negative 9.8. And then your delta X, whatever that is, whatever the distance is they give you, you plug in there too. So that would be your work done by friction. The work done by the applied force is the same thing, but it's just this force multiplied by delta X, whatever this force is. And then
My
the
only
total-
problem is since it's going at a like consistent velocity, I don't know like how to find the force that way because I'm so used to it, just the mass
Oh.
times acceleration.
Well, it is. So the sum of the forces in the X direction has to equal 0, right? Because it's at a constant velocity. And you have the applied force forward and you have the minus friction backwards, and that has to equal 0. That means the force pulling forward is equal to the friction. So you can calculate the frictional force. That's going to be your pulling force as well. It's just going to be positive. So your friction, this is going to be equal negative the friction essentially. So that's how you
I mean, I get that part that the work of applied force and the work of friction are going to be more or less the same, but when I put in 0, it doesn't take 0. I'm trying to find like, I don't know how to.
Which one are you calculating? Are you calculating A, B, or C right now? Which one are you not getting right?
A.
Okay, so for part A, your friction, your force, your applied force is not 0. It's equal to the friction force. So whatever you calculate for your friction force, you need to plug that in for big F. So let's say in my case, I have my friction.
Oh wait, so
coefficient is
friction
30.
force is also going to be applied force in this problem.
Yeah, they have
So
the same magnitude. Your friction pushes back on the box as much as you're pulling forward on the box.
Okay.
So they're the same magnitude. So the way to do this problem is to calculate the friction first. And then whatever that number is also your force for F. That's also your applied force.
Except in this case, work by friction would be negative and then work by applied would be positive.
That's correct. Just like
Okay.
the direction for the
So-
friction is negative and the direction for the applied force is positive.
So if we were to use this problem, it would be, let's find the normal force again.
So if you got, let's say that you got 20 newtons of friction, you're also going to have 20 newtons of applied force because they cancel each other out to give a constant velocity, right? But the 20 newtons would be multiplied by the distance, in this case, 30 meters, right?
Times the displacement.
There's actually another problem. There's actually something else that you need to do in this problem that I didn't consider because I didn't see at the end. It says
Oh,
that
because
the
it's at an
force-
angle.
the force is directed at an angle. So we need to actually redo all of this really quick because it's going to change everything.
Okay.
And this is how it's going to change it. This force that you're pulling with is at this angle like this now. Friction is still like this, but
So
you're going to have two components to this force now, right? And that means you're going to have a weight pulling down. You're going to have a normal force up, and you're also going to have this force up. So in the y direction, you're going to have 3 forces. So the sum of the forces in X looks like this. It's going to look like the force applied times the cosine of theta minus friction equals 0. So now that's going to be a little more complicated to calculate F, big F. You're going to have the sum of the forces in the y direction is going to equal the weight down, so negative mg. Then you're going to have the normal force up, but you're also going to have the force sine theta up from the applied force. In essence, by lifting the box upward a little bit, you're actually reducing the normal force. You're actually helping the box along by lifting it up off the ground. So that so in the end, when you calculate the normal force here, your normal force is now going to equal mg minus f sine theta. So that's going to give you a different normal force, which is going to translate to a different frictional force, because friction equals mu times n, right? So that's going to give you a different frictional force. And that is going to give you a different, once you've calculated the frictional force, then you'll put the frictional force in up here, and you're going to have to calculate the applied force, which will be very different as well, right? So essentially you have two equations with two unknowns. The two things you don't know are the applied force and the normal force in each case.
So what would I do then, like considering like
What I would do, this is what I would do. I would replace the friction in this top equation with mu times the normal force, because that's what it is.
mhm,
And now I have two equations to solve. Normal force equals mg minus f sine theta, and this equation here. This one equals 0, right?
mhm.
And I would plug one of these into the other because you have two unknowns. Probably the easier one to plug in is to plug this one in. So if you solve this one for the normal force, right here, you get normal force equals f cosine theta over mu. If I plug this one into this equation right here, actually that doesn't really help either, because then you get a cosine theta and a sine theta in the same equation. And that's not always easy to mess with. I mean, you can do it, but I wouldn't recommend it. What I would actually recommend is solve both of these equations for f sine theta and f cosine theta. So this one's already solved. If I put the mu back over here, then you have this equation like this: mu n equals f cosine theta. And then solve this one for f sine theta. So you get f sine theta equals that'll be mg minus n, I think, like that. That looks right. So then you then divide the two. When you divide the two, then you're going to get f sine theta over f cosine theta equals mg minus n over mu n. And this is just a number because the f's are going to cancel and you know what theta is, right? So this is just going to give you a number, and this, then you can solve for n. Then once you solved for n, you can go back and plug n into either one of these equations to solve for f, and then you'll be done. Well, then you have to calculate the work from there.
I was gonna say, well, after all that, the calculating work would be easy.
Yeah.
Yeah, I'd been spending all this weekend trying to scrambling for a solution. I didn't realize.
I didn't see right away that they were pulling in an angle. If they weren't pulling in an angle, this would be a much simpler problem. But that causes this particular thing causes us to figure out. We have to figure out that angle, figure out what that angle does to things, and then.
Here, I'm gonna take a picture of all this that you worked out here. Yeah, no, it's all right. I don't know.
Let's see what their hints say. Are their hints very helpful? Sometimes they are. Sometimes they aren't. Work, applied force. You probably need to figure out what applied force is first. Yeah, that's not a very good hint, but it's correct. Once you know the answer to part A, is there a shortcut to getting the answers to part B and C? Yeah, so that's actually a really good, that second hint's a really good hint, because all you really have to do is calculate the work from one of these forces, right? And you already.
And then you can get the others, yeah.
Yeah, because the other one is just the negative of the first one, right?
And
Well, in X. So if you calculate the applied workforce, then you're good to go. If you calculate the applied friction work, you can do that, but to do that one, you have to know the applied one because the friction depends on the applied force, right?
Mhm.
So to do the first one, you figure out the applied work, applied force work, then that's equal to the negative of the applied friction work, because it's just in the opposite direction. And then the total work, of course, is going to be 0.
Yeah. You talking about the advice you gave when I asked for help a couple days ago did help with me finding the total work, but it just
It did
Yeah,
help or didn't help?
well, it did help. Like, it made me realize that the total work and the work done by friction would it helps me find those. But
Yeah.
I just well, I don't know.
So here, this is my take on energy. And it's one of the reasons that I don't like to teach energy first. Energy is very simple to calculate mathematically in the end. The math of energy is simple, but sorting it out in your head is not very simple. Like trying to figure out what energy is going where and why, and positive, negative, this kind of thing. That I think is a fairly complex exercise in sorting out what everything is doing. And so I don't prefer to I don't prefer to start off my class with that for that reason. I think that it gives people an unhealthy
They set their expectations
Yeah.
from it for it being easy, and then the rest of it comes in. Yeah.
much harder. Yeah. I think that's whereas, doing kinematics and forces, the math part is a little bit harder, but sorting things out is a little bit easier. I think it's better for the brain to learn how to sort out a system and then do the math, even if the math is a little bit harder. But that's just my opinion.
Mhm. All right.
So is that enough for you to understand and finish it up, or do you have any other questions?
I'll try this out. If I still can't get it, then I'll ask.
Sounds
I'll
good.
send- Yep.
We'll see you
Thank
later.
you.
Bye.
Yep. Have a good
Thank you. I
day.
was stuck on that one too.
What's that, Taylor?
I said thank you. I was stuck on that one too.
All right. Well, we're all good to go then.
Yep.
See you
Have a
later.
good day.
You too.